Okay, yesterday while discussing the classification of positioning, I forgot to mention that in this class we are concerned with continuous real-time self positioning or a navigation of a moving vehicle. Okay, but whatever we'll be discussing will also hold for other categories. But we are particularly interested in this kind of navigation. Okay, continuous real-time self-navigation of a moving vehicle. Today we are going to start the discussion of navigation techniques. So there are primarily two navigation techniques. They are called dead reckoning and position fixing. Okay. Now under position fixing, there are five more. They are proximity, ranging, angular positioning, pattern matching, and Doppler positioning. We are going to discuss all of these methods one by one. Okay, starting with dead reckoning. What is dead reckoning? Now, if you look up the dictionary, you will find that dead also means perfect or exact, and reckon means measure. Okay. So, a dead reckoning device is intended to provide perfect measurements. Okay, this is not possible. No device can provide 100% accurate measurement, but probably that was the intention behind developing such a system. And that's why probably it was named that way. We can only guess. Such explanations are not given anywhere. So how does it work? Now it measures the change in position or velocity or acceleration and integrates it to get the change in position. And this change in position can be added to the position of the vehicle at the previous time instant vectorially to get the current position. Okay. Examples of dead reckoning systems are pedestrian dead reckoning system and odometer. There are other examples also. I've just noted two of them here. So what is a pedestrian dead reckoning system? A pedestrian dead reckoning system has accelerometers. All of you are familiar with accelerometers? Yes or no?
Yes, ma'am.
How about others?
Yes, ma'am.
Ajita, Nilay?
Yes, ma'am, yes.
Okay.
Yes, ma'am.
So it has accelerometers mounted on the body, uh, usually on the feet. Okay. So whenever a step is taken, step initiation happens. There is a change in accelerometer measurement, and comparing that against a threshold, we can detect whether a step is taken or not. So steps can be detected, and then by counting the number of steps and multiplying it with the step length, we can find the distance traveled by the person. Now we can use some default step length, but for better accuracy we can also model the step length based on other information such as whether it is a flat terrain or some uneven terrain, slanted terrain or hilly terrain, whether the person is carrying any weight or he is simply casually walking or whether he is running. So things like that, if we can incorporate, we can model the step length more accurately, and that will give us a much better measurement of the distance traveled. So distance traveled is the change in position, and by adding that vectorially to the previous position, we can find the current position. The next example is odometer. So odometers are used in cars to find the distance traveled. So it has a ferrous tooth wheel, okay, made of magnetic material, and the wheel is mounted on the transmission shaft or the wheel axle of the vehicle. So as the vehicle moves, the transmission shaft rotates and the wheel, the ferrous wheel also rotates along with it. There is a sensor, magnetic sensor. Okay, as each tooth of the wheel passes through the sensor, its flux density changes and the sensor sends out a pulse. Okay, now it is known how many teeth are there on the wheel. So we can, in one complete rotation of the Ferris wheel, we'll know how many pulses we'll get. Dividing that, uh, I mean, the total number of pulses sent out by the sensor can be divided by that number to get the number of rotations of the vehicle wheel. And that is proportional to the distance traveled by the car. So this is how we can find distance traveled by the car using an odometer. Now, we should also note that we need to add these two quantities, previous position and the change in position, vectorially. So they are vector quantities, right? Now, in what frame, coordinate frame, do we have the previous position? So previous position means we need to select a particular body frame, body coordinate frame. So when we discuss navigation coordinate frames, we'll talk about the formal definition of body frame in the context of navigation. For the time, we just note that frame is defined, which is attached to the body, so it has an origin at a suitable point, whose position we are interested in finding. And then three orthogonal axes. Typically, we consider right-handed orthogonal coordinate frame. So, we are interested in finding the position of the body axis origin, body frame origin. And this is defined with respect to some external frame. It can be attached to the surroundings, it can be some global frame, okay? But we are interested, fixed to that. We are interested in finding for terrestrial navigation, we are interested in finding the position of this origin with respect to an external frame. So we are going to define different frames later. For the timing, just assume that there is an external frame, reference frame, with respect to which we get the components of the position. How about the change in position? A change in position is again a vector quantity. It depends on how the sensors are mounted. Because a sensor can only measure a quantity along its sensitive axis, right? So, a change in position will have its components along the sensor sensitive axis. So let's call that sensor frame. Okay. Now sensors are mounted on the vehicle body. So we can predetermine the sensor frame orientation with respect to this body frame orientation. Okay. So the sensor frame orientation with respect to the body frame is predetermined. Now for simplicity, let's assume that they are aligned. Okay, the sensor frame is oriented with the body frame. This means we know the change in position along the body frame axis, right? But the previous position is known with respect to this external frame. Change in position, let's say in this 2D case, this is the external frame. So the previous position is known with respect to this external frame resolved along the frame axis. Whereas change in position is known in the body frame, right? Now, unless we know the orientation of the body frame with or attitude of the body frame with respect to this external frame, we will not be able to add these two quantities, right? Therefore, to do this vector addition, attitude is very important. Attitude plays an important role here, which is evident in this simple 2D case. So we need to add these two quantities, and we know the components of this vector only along this direction. Unless we know the orientation of this frame with respect to this one, we will not be able to add these two vectors, right? So it's important to know the body frame orientation or attitude with respect to that external frame. Now it can also be possible that the attitude changes if the body frame orientation changes and the attitude also changes. When attitude changes, we need to keep the integration step size small. The smaller the step size, the better is the accuracy. Okay. Now, when we say orientation, what exactly we mean? Now, in this simple two-dimensional case, only heading is required. What is heading? How do we define heading? So let's assume that this is north, local north. So this is along local north. Then the angle that the body, let's say this is the body x-axis, then the angle that the body x-axis makes with the local north or the body frame orientation with respect to the local north, that actually gives the heading. Okay. We are considering only two-dimensional case here. Now, how do we measure heading? Heading can be measured using magnetometers or magnetic compass. Okay. A magnetic compass will deflect the needle along the local north, magnetic north. Now, if the latitude and longitude are known, then we can find the deviation of the magnetic north from the local north. Okay, there is a magnetic chart which helps us find the angle between magnetic north and local north at each latitude longitude. So by applying that correction, we can find the heading with respect to local north. In case of magnetometers, the Earth's flux density, magnetic flux density is measured, and then using some methods, and this measured flux density, magnetic flux density, we can find the heading. Okay. But how about three-dimensional motion? In case of three-dimensional motion, we require heading elevation bank. Heading elevation bank are equivalent to roll pitch yaw. We call them heading elevation bank when we are defining them with respect to north, east, and down frame. Okay, so heading is equivalent to yaw. Elevation is equivalent to pitch, and bank is equivalent to roll. So basically, we to define attitude or orientation, we require roll, pitch, yaw, or heading, elevation, and bank. Now, in inertial navigation system INS with 3 accelerometers and 3 gyroscopes, typically they are mounted on the vehicle body. That's called a strap down configuration. They are fixed to the body. Is a complete 3D dead reckoning system. Okay. Why we say complete 3D dead reckoning system? Because from an INS you can get everything. Okay, you can find position, velocity, both linear and angular, acceleration, both linear and angular, and then also attitude, roll pitch can be obtained. The accelerometers not exactly measure acceleration. It's called non-gravitational force per unit mass, specific force. Okay, with respect to inertial frame, we are going to define inertial frame later. And then gyroscopes measure angular velocity of the body with respect to inertial frame. By integrating angular velocity, we can get change in attitude. So with the help of 3 gyroscopes, we can find complete attitude, roll pitching, or heading elevation bank. So INS is an example of a 3D, complete 3D dead reckoning system, inertial navigation system. What are the advantages of a dead reckoning system? It has high update rates, get measurements at a very high rate. In case of INS, measurement update rate is somewhere between 100 to 1000 hertz. Okay, low short-term noise. Over a small interval, noise is low. The noise is basically the random error which gets added to the measurement. Okay, we call it noise. It has to be modeled statistically. So it has low short-term noise. It is self-contained. Typically, dead reckoning system is self-contained. What does it mean? Now see, if you consider an inertial navigation system, it does not depend on any external information, right, to measure the quantities, acceleration or angular velocity. So using those sensors on its own, it can measure uh, the parameters or make measurements. So it is self-contained. Typically, dead reckoning systems are self-contained. And you can get all navigation outputs. So there are dead reckoning systems, for example INS, which can give all navigation outputs. There are disadvantages as well. The first one is errors grow with time. So although dead reckoning systems are self-contained, because of this problem, it is not possible to use them independently over time. So depending on the quality of that system, we need to use other system alongside. Okay, so integrate them. Otherwise, we will not be able to arrest the error growth. Why does the error grow with time? This is because we are finding change in position. So we have some previously computed position which is not accurate, which has some error to it. To that, we are adding some change in position, right, which we actually obtain by making some measurement. So change in position also has some error in it, and we are adding these two quantities. So what will happen? The resulting change after the vector addition will have more error, which is pictorially shown here. So as we keep integrating the error circle, so this circle here shows the uncertainty. So error circle grows in size, which means errors grow with time. So as errors grow with time, after some time, depending on the quality of the sensor, anything that you get from it becomes useless unless you do something intelligent to bound the error. And that is generally done with the help of other sensors which do not have this kind of issue. So you need to use another sensor which complements it. Another issue with dead reckoning system is that since you are doing integration, initially the navigation solutions must be initialized. So if you start with some position, initially you are measuring change in position, right? And that has to be added to some previous position. So when you start the system, in the beginning, you need to provide initial solutions. So the solutions must be initialized with the help of some other means. So these are the disadvantages of dead reckoning. Any question on this?
No, ma'am.
Okay. We are going to see position fixing now. Now, unlike dead reckoning, position fixing uses external information or signals coming from transmitters, transmitters external to the body, or some features, environmental features to determine position. So it depends on external information. So for position fixing to happen, external information or signals coming from outside are important. What are the advantages? Good long-term accuracy, no error rate. We are not doing any integration here. We are making measurements and using the measurements we are getting the position. So it has good long-term accuracy. So this is complementary to dead reckoning because the former one has errors growing in time, whereas this has good long-term accuracy, errors do not grow with time. What are the disadvantages? It depends on external information. It needs to receive signals from outside. Now signals can have some distortion. Signals some anomalies may corrupt the signal because signals are coming from outside. For example, in case of GNSS, signals are coming far away from satellites. If something wrong happens on board the satellite, then wrong signals will be received by the user. So signal anomalies can corrupt the measurement and the navigation solution. Now, depending on how strong the signals is, signals can be attenuated while traveling. For example, in case of GNSS, signals are weak. Signals are coming from satellites and satellites cannot pump in too much power. It has limited capability. So it only can pump some limited power. And signal has to travel a large distance, thousands of kilometers. So weak signals are received, and if there is an obstruction, signals will be attenuated, may not be received also. Now we saw that in case of dead reckoning, attitude is an important. So we need to have a means to find the attitude. So a complete dead reckoning system gives attitude. Whereas in case of position fixing, attitude determination is possible, but not as easy as dead reckoning. So you need to do something more to get attitude from position. Not all the systems will give you attitude, but some systems do. But for that you need to make a special setup. For example, in case of GNSS, you need multiple receivers. Receivers are basically user equipment used to receive signals. Transmitters transmit signals, and receiver receive signals. So you need to use multiple receivers. You need to process signals in a particular way. You also need to know the relative distances between the receivers. So you need to make a separate setup to get attitude from position fixing method like GNSS, what GNSS is. There are 5 types of position fixing methods: proximity, ranging, angular positioning, pattern matching, and Doppler positioning. We are going to discuss one by one all of the 5 methods. The first one is proximity positioning. What is proximity positioning? It's not so accurate. It's a crude way of finding the position. Suppose you are standing in front of a famous building or a known landmark, then you know that you are in an area surrounding that landmark, right? So this is what is shown here. This is the landmark, and if the user is here and he sees the landmark, he will know that he is in an area surrounding that landmark. This area is called containment zone. It's a different use of containment zone, of course. And then when he sees another landmark, he knows that he is at the intersection of these two containment zones. Right? So as he sees more and more landmarks, the intersection will reduce in size and he will better know his position. But again, this is a crude way. You just see the landmarks and you know that you are at a place where you can see all these landmarks. Okay. Next is ranging. In case of ranging, uh, the distance between the user and transmitter is determined. So we can call it a landmark or transmitter. User can be denoted as receiver also, because it has an equipment to receive signals. So we can interchangeably say user or receiver, and in place of landmark we can say transmitter. So basically they denote the same thing. There is a landmark transmitter. Basically we are receiving some signals from it. Okay, so either we can say user or receiver, or and here we can say transmitter or landmark. Generally we will use the term transmitter. So in case of ranging, we are interested in the distance between the user or receiver and the landmark and transmitter. So suppose in this case the transmitter is here and the user is here. So he receives signals from the transmitter and he finds the distance uh, between him and the transmitter. Uh, so for a given distance measured, he can be anywhere on this circle whose radius is equal to the distance measured, and the center is at the transmitter. So he can be anywhere with a given measurement from a given transmitter. He can be anywhere on this circle, right? Now the locus of the user position at which uh, the measured quantity is constant is called line of position in 2D. So for ranging, the measured quantity is generally range. So the line of position for constant range is a circle in 2D. Now if we extend this to 3D, then the circle becomes sphere. We no longer have a line, we have a surface, right? It becomes a sphere, which is called surface of position. So in case of 2D, we have lines of position. In case of 3D, we have surface of position. So for constant range measurement, the line of position is a circle in 2D, and uh, the surface of position in 3D is a sphere. Right? Now, if the user receives measurement from signals from another transmitter, he will get the range to that transmitter also. Then it implies that he is at the points of intersection of these two circles, right? We know there are 2 points of intersection, right? So he can be either here or here. There is an ambiguity, correct? In 2D, there is an ambiguity. Here we are seeing it in 2D. So he can be either here or he can be here, right? So we need to resolve the ambiguity. How can we do that? So if we have some prior information, like the user can be somewhere in this region, then we can discard this one. So either using prior information or an additional measurement, we can resolve the ambiguity. So we receive measurement from another transmitter, signal from another transmitter, and that gives us another circle. And we know that 3 circles intersect at a particular point, and the user must be at that point, because he is receiving signals from all these 3 transmitters. So in case of 2D, we need a minimum of 3 transmitters if we want to find the position unambiguously when we do not have any prior information. This is clear to everyone? Now, how about 3D? What do you think we'll have in 3D? What is the minimum number of measurements do you think will be required to find the position unambiguously in 3D with no prior information. And why?
It's both, man.
If you already know, do not answer, okay? Let everyone think and then. How about others?
Yes, ma'am, 4.
Now, why do you think 4?
Ma'am, if you have 3, then there are 2 possible positions. So we need a fourth one to find out which one.
Yes. So if we have 3 transmitters, we get 3 spheres, right? Now we know 2 spheres will intersect in a circle. So from 3 spheres, we are getting basically 2 circles. And 2 circles will give us 2 possible positions. So to resolve the ambiguity, we need to add one more transmitter. So minimum of 4 transmitters is required in 3D if we do not have any prior information. If we have prior information, then we can remove one that additional transmitter. Okay. So any question up to this?
No, ma'am.
Okay. Now on the previous slide we saw just one circle. But is this just one circle?
Ma'am,
Yes.
I didn't understand how we need 4 transmitters for a 3D orientation.
It is not orientation, 3D position. Okay, we are finding the
Okay, okay.
position in three dimensions. Okay, you understand how it can be found
Uh,
in 2D,
2D I
right?
understood. Yeah.
In 3D, in place of circles, you have spheres, right?
Yes, ma'am.
So two spheres will intersect in a circle. Yes or no? Two circles intersect in 2 points, right? How about two spheres? Just think about it. You need to visualize. You just think of two spheres. They are intersecting. So how will they intersect? It is always a circle.
Okay, ma'am. So, for 3 spheres, we get
Two
two
circles.
circles. Okay, okay, understood.
Okay. Okay. Now see, on the previous slide you mentioned that we make a measurement corresponding to a transmitter, and uh, for a given measurement the user can be anywhere on the corresponding circle, right? But the measurement is never accurate, right? So whenever we are making measurement, calculating or measuring the distance to a transmitter, that distance measurement, so this straight line distance is also called range, okay? So that range measurement always has some errors. So the measured range is equal to true range plus some epsilon term, okay? And that epsilon we never know uh, deterministically. We can only predict a bound in a statistical sense. We can say that, okay, with this much probability, this epsilon term will lie within this range. We can only associate a bound statistically to this epsilon term. So this implies that corresponding to any measurement, basically the user will be within a band of circles. It's not just one circle, because we have this bounded epsilon term which is expected to lie within a range associated with any measurement. We have a band of circles, right? It's not that we have just one circle. We make a measurement, we have one circle. And we know that true range is equal to, measured range is equal to true range plus epsilon. So there will be one circle which corresponds to true range, right? We do not know which one is that. We can only say that around that circle we have some plus minus addition or subtraction, because the epsilon term will be within that bound, and then we get a band of circles, right? So this is for one particular measurement. For another measurement, again we get another band of circles. And now these two bands intersect. So instead of getting a particular point, we are actually getting an area. So if you consider the two bands, these two bands, this one and this one, we basically have this as the area of intersection, correct? The user can lie anywhere within this area. This is called area of uncertainty. Similarly for this also, instead of having a point, now we actually have an area where the user can lie, right? Now if we had one more transmitter, then we need to consider the intersections of all the three bands of circle. So if you consider the third one, then this area of uncertainty is reduced to this rectangle shown here. This rectangle shows the area of uncertainty of the three bands of circles. This one. So with another transmitter, we have been able to reduce the size of the area to some extent, right? Now our objective is to reduce this area of uncertainty to the extent possible. How can we do that? So on the previous slide, we saw that minimum for 2D, minimum 3 measurements are required to unambiguously find the position. But here we see that by adding three bands of circles, we have been able to reduce the area of uncertainty. So if we can have as many transmitters as possible, there is a higher chance that we will be able to reduce the area of uncertainty. Another way of reducing the area is to have narrow bands of circles. How can we get narrow bands of circles? If we can reduce the bound of that epsilon term. So if we can have good quality measurements, then epsilon will lie within a narrow range, narrow bound. It will have a narrow bound. And then the thickness here also will reduce. So as the thickness reduces, the area of uncertainty will also reduce. So by having as many transmitters as possible, we can reduce the area of uncertainty, provided we have good quality measurements. So if you add more transmitters, but they all have these thick bands, then definitely the area of uncertainty will not reduce. So we need good quality measurements. We also need as many transmitters as possible. Now, as we have more transmitters, there is a higher chance that we have more good quality measurements. So, although there is a minimum number of measurements, theoretically, to reduce error and improve accuracy, we want as many transmitters as possible. And we also want good quality measurements with low error or low noise. Now, do you think there could be anything else that can affect this area of uncertainty? If you already know, do not answer, okay? If you have already read, do not answer. But can there be any other way by which the area of uncertainty will increase or decrease other than narrowing this band or adding more measurements? Can there be any other way by which we can increase or decrease the area of uncertainty? What do you think? Does the area depend on how they intersect? Does the area depend on how they intersect? Yes. And
The landmarks are closer
landmarks are,
closer to one another.
I did not understand. What did you say? Landmarks are?
If the transmitters, if they are closer to each other.
Transmitters are closer to each other, okay. So it is possible that they intersect this way in a skewed manner like this. They can intersect almost orthogonally, right? Now when they intersect almost orthogonally, then only we can reduce the area of uncertainty. So it depends on how the transmitters are distributed with respect to the user. If they are spread away in all the directions, distributed uniformly in all the directions around the user, then there is a higher chance that we get better accuracy because they will intersect this way. But if the transmitters are all on one side, they are close to one another, then there is a higher chance that they will intersect this way. So the distribution of the transmitters around the user is also important, and this is called signal geometry. Okay. So in case of ranging, we want as many transmitters as possible. We want good quality measurements. We also want transmitters such that they are well distributed around the user to improve signal geometry. Okay. Any question? Okay. Next, let's see how the range can be determined. Some example. The first method is called time of arrival. This is used in GNSS. So GNSS is a position fixing system. Okay. Now, in this case, there is a receiver on board the user vehicle. The user will have the receiver which receives signals from satellites. It is a passive system because it does not send signals to satellites. It can only receive signals from the satellite. Okay, so signal travels only from the satellite to the receiver, which is called one-way ranging. Okay. Now, when the signal starts from the satellites, it is time-stamped. Satellite has highly accurate atomic clocks. Okay, the signal is time-stamped when it starts from the satellite. Now, when the signal is received by the receiver, there is a clock, although not as accurate as the satellite clock in the receiver. It's an inexpensive clock, but it also timestamps the signal. Okay. So by processing the signal in the receiver, it is possible to find the time of transmission of the signal. Okay, and then by time stamping the signal, when it arrives at the receiver, we get the time of reception. And the signal travels at the speed of light. Okay, although the speed is not the same as the speed of light in a vacuum when it travels through the atmosphere. So it has to pass through the atmosphere to reach the receiver. Then the signal speed, propagation speed changes. Okay, so that introduces some additional error time. Now, if we subtract the time of transmission from the time of reception and multiply that to the speed of light, we get the range, correct? Now, see, this clock is not an accurate clock. To get the correct range, it is important that we need this time calculated accurately. Now see, this is multiplied with the speed of light. So any small error, even millisecond error, will result in kilometer level inaccuracy. So it is very important that we measure the time accurately. Now satellite clocks are accurate, moreover they are also monitored. Okay, the signals also have information about the satellite clock error. So by applying all these, it is possible to calculate this time of transmission accurately. But that is not the case for the time of reception. Now, this delta TU term actually accounts for the error in the time of reception. So you can think of the actual time of reception, which is provided by the user, is equal to true time of reception plus some error delta TU, and then take delta TU outside, so you get C times delta TU, and this one is TR minus TT times the speed of light. So this is an additional term that you get because the receiver has an inexpensive clock and this is not known. So we have an additional unknown term. Okay. And then when we are making measurements, there will always be some noise. In addition to noise, because the signal travels through the atmosphere, some additional error terms also get added. Okay. So we can write this range as this one plus this additional unknown term, and all other errors are grouped in this epsilon term. Okay. Um, yes. Any question?
And can you explain why the two error terms? Why can't we take using one single?
I'm not able to hear you properly. Can you speak loudly?
I mean, am I audible now?
Yeah, better.
Yes, ma'am, I was asking, why do we need two error terms?
Why do we need two error terms?
Two, yeah,
You mean this and this?
yeah.
See, this one accounts for inaccurate calculation of time of reception. There are other errors as well. As we go on, this will be clear. So there will be noise. Whenever you are making measurements, depending on the surrounding environment, some noise will also be received by the unwanted signals, noise, etc. will also be received by the receiver. Then when the signal travels through the atmosphere, its speed of propagation gets changed. But when you are doing the calculation, you assume that the speed of propagation is equal to speed of light in a vacuum. So you need to include some additional terms to account for the change in speed. Okay. When we talk about the effects of the atmosphere, this will be clear to you. Okay. In fact, at the end of the discussion of navigation techniques, I am going to give you an overview of GNSS. There also this will be clear to you. Okay, why we require additional terms. Okay. So this is for one-way ranging. Next is two-way ranging. So we can also calculate the time of arrival using two-way ranging method. Example is distance measuring equipment DME, which is used by aircraft. Okay. In case of DME, what happens is there is a transmitter on board the aircraft. It's called an interrogator. Okay. The transmitter sends out an interrogation pulse pair, okay, at some particular frequency. Then this is a ground-based navigation aid. The base station, DME base station, is located on the ground. So when it is within the range of the DME base station, this pulse pair is received by the base station. Okay. Then the base station, after receiving the pulse pair, waits for some particular time. Okay, there is a wait time, and then it sends back uh, another pulse pair at a different frequency. Okay, the interrogator on board the aircraft receives that pulse pair. Now it knows when it transmitted the interrogation pulse pair. It can also calculate the time of arrival of the return pulse pair. Right? So by subtracting these 2 times, it can calculate the round trip time, right? Round trip time of the signal. Now, unlike GNSS, here the signal is transmitted by the user. So this is an active system. This is a passive system. This is an active system. Okay. And since the signal travels in 2 directions, back and forth, we call it two-way ranging. Now, what is the range in this case? So TR is the time of reception. We also call it receive time. Okay. And TT is the time of transmission. So TR minus TT and minus this delta T, the wait time of the base station. So it waits for some time. Depending on base station, it will be either 50 microsecond or 56 microsecond, and then saves back the pulse pair. So that also has to be subtracted. So TR minus TT minus that wait time will actually give the round trip time of the signal. That multiplied with the speed of light divided by 2 will give the range to the base station. Okay. And again there is an epsilon term to account for errors. Now see, in this case, although the aircraft has an inexpensive clock, it is not required that we need to account for this additional term. Why? The same clock is used to report both the times, and we are subtracting them. And generally the aircraft to receive signals from the base station has to be within a few hundred kilometers. Okay, so the round trip time is also not large, and the clock deviation over this round trip time is small. And we are subtracting 2 times. Both have errors and we are subtracting them. So in this case, we more or less nullify this delta T, the uncertainty. If there is any residual error, that can be modeled here statistically. Okay. So by having two-way ranging, we can get rid of this additional unknown term. Okay. Now, how does it help? See, we discussed that in 2D, we need minimum 3 transmitters. If we have an additional term, see earlier we had 2 unknowns, right? In 2D we had only X and Y coordinates, 2 unknowns, and we needed 3 transmitters. Now in this case we have an additional clock, which means we have 3 unknowns. So we need 1 more transmitter. So in 2D, if we want to find the position unambiguously, we need a minimum of 4 transmitters because we have an additional unknown clock error term, right? But in this case, we do not have that additional term. So here in 2D, a minimum of 3 transmitters would be required. Okay. In 3D, in this case, we require a minimum of 5 transmitters. Whereas here we require a minimum of 4 transmitters. Now, for DME, unfortunately, we cannot find height of the aircraft because see what happens, this aircraft, they will be generally to receive signals, basically the service radius of the base station is few 100 kilometers. So the horizontal distance will be much more than the height. Height will be within say 15 kilometers, whereas this horizontal distance will be about 100 kilometers or more than that. Now, Since this vertical distance is much smaller than the horizontal distance, it can be shown that the height that you derive using the DME measurements is not of good accuracy. Okay. So using DME, we can find only the two-dimensional position. We do not use DME measurements to find the height because the geometry in the vertical direction is not good. All the stations are based on the ground, down the aircraft, below the aircraft. So height accuracy is not good in case of DME. Okay. In case of GNSS, we can find 3D position. Okay, satellites are far away, located far away, but the height accuracy is not as good as the latitude and longitude accuracy. Because again, all the satellites will be on top. Okay, but here the geometry is much better than this one, and therefore we can derive height accuracy. GNSS does provide all the three coordinates, okay, latitude, longitude, and height, or XYZ position. I think that's it for today. Let me ask you one thing. Actually, some construction work is going on. Are you hearing any noise? Or you are able to hear my voice clearly?
It's clear only.
Okay, fine.
Ma'am, it is clear, ma'am.
Okay, that's it for today. If you have any question, we can take one or two quick questions. So are you following what I'm saying, or I'm going too fast, or you want things to be done in a different way? If you have any comment, you can tell me.
It's all right, ma'am.
We'll meet tomorrow. That's it for today.
Thank you, ma'am.
Thank you, ma'am.